Hey guys, how we doing today? And today we're going to talk about Continental Drift. Obviously, it didn't always stay Continental Drift. There's another name, Plate Tectonics, all right, which I will be saying later on. So just let's see how we got there. All right, so first thing, turn of the century, 1912, Alfred Wegener. All right, was a German scientist, that's actually how to say it, Wegener, proposed the Earth's continents are moving around the Earth's surface. What he looked at, of course, puzzle piece fit. So he took all the continents, he cut them out, and he put them together as a puzzle piece. Is basically the first two continents that all right away stand out. Africa and South America. You can see they look like they interlock very well, and then North America kind of fits in there too. So that thought right there kind of convinced this must have been together. All right, obviously we can't just stop at that. So let's see what he developed over time, and other scientists also. All right, so 200 million years ago, all the Earth's land masses were connected to form a supercontinent called Pangaea. All right, so that's what he named it. It's all Earth in Greek, and that's what developed this. All right, so let's see where scientists went next. All right, one thing I'm going to remind you: Earth Science Reference Table. Okay, and this is on page 8. We'll be using this in a future chapter with fossils. But this also shows you the position of land masses during certain time periods. So it tells you how many million years ago here, and it tells you the name of the geologic period, all right, which we'll talk about. So Triassic period is when Pangaea formed, all right, and through the dinosaur age, obviously, and then ended up going back to where it is now in its current position. Okay, video of Pangaea breaking up, definitely watch it. See which continent moves most, or part of a continent, I should say. And there's a certain mountain range that's formed in that area. So no coincidence, right? We'll talk about that in a future slide. Okay, so here's also some other looks at the continents. They named them different things during different time periods also. So Pangaea was everything. Laurasia was Europe and North America together in Asia. Gondwanaland was basically South America and Africa. Okay, so you can see the different names they gave to them. All right, now, so evidence that came along with Wegener's thing. So certain continents fit together like a jigsaw puzzle. Some fossils are found on separated continents, such as Mesosaurus, which is actually a relative of our current day alligator. It was found on South America and Africa, and it's no Olympic swimmer, so, and even an Olympic swimmer can't do this. Couldn't swim across the Atlantic Ocean. So therefore, those continents had to be closer, maybe even just a shallow body of water between them. But definitely they were touching at some point. Warm climate fossils and cold beds found in Antarctica. All right, so places that are really cold. So the only way that could be true, those had to be closer to the equator and possibly warmer at some time in history. Okay, also we can look at the rocks and mountain ranges. Okay, so mountain ranges and mineral deposits found on separated continents, and they match up well. So a perfect example of this are Appalachian Mountains, which are on the east coast of the United States. Match up to the Caledonian Mountains, which are up in Scandinavia, Sweden, Norway area. Pretty well in rock type, age, everything. So that tells you maybe they were once one big mountain range. Okay, so we look at that, we see that in a few different areas of the world. All right, so here's like kind of like the matchup picture here. So again, matching rock types in common. You can see different areas that match. Also, South America, Africa, as I mentioned. A lot of animals that came across between those two, so that's definitely good evidence. And even Antarctica being interlocked up here. So there's a lot of commonalities between animals or fossils left over of them. Okay, problems with Wagner. Well, we didn't have the technology to do all the exploring we need to do. So Wagner did not consider what's called the oceanic crust because he didn't know about it really. He didn't have the means to study it. All right, we didn't have submarines. Okay, and that was the big invention that really led to a furthering of this this study, basically. All right, so Wagner did not explain what force was moving the continents either. So he just had the continents kind of floating around, did not know why they were moving. Of course, we figured this out later on. And so continental drift was a theory that was kind of rejected, revised, revamped, and then became what we know as the theory of plate tectonics, right? Because it's not just the continents doing the drifting, it's the full plate. All right, so let's take a look at this. What went further with this? Okay, this is the reference table, page 5. So again, you'll see all the different types of plate boundaries, which we're going to talk about later in the notes. Divergent plate boundaries, meaning moving apart. Convergent, coming together. Transform, moving side by side. Complex, uncertain, there's too much going on in that area, so we can't determine the motion as well. Relative plate boundary motion, so they tell you the arrows in certain areas. Mantle hotspot, that's a weak part in the crust. We'll talk more about what happens there. The one I do want to point out, which is coming more common on Regents questions, are the convergent plate boundaries with, you notice it says subducting plate and overriding plate. Okay, so if they ask you for the overriding plate, you see the way the box symbol is, you go the opposite side of that. So in other words, if you go to the Peru-Chile trench zone, the Nazca plate is the subducting plate, and then the overriding plate would be the South American. So I'm just showing you that because I've seen more and more of that on the Regents as of late in the questions. All right, mid-ocean ridge. Okay, this also is a symbol on there. Okay, so make sure you're aware of that. Oh, and one more thing about this chart. Look up here. Here's the prime meridian. So this side is east of the prime meridian, which wraps around to the other side of the world till you get to 180, the international date line, and now you're in the west. So these are all degrees west from 0 to 180 here. So just be aware of that. That's easy to mess up if you're doing latitude, longitude on this map. All right, what's driving the plate movement? Definitely convection. Okay, and it's convection of basically the magma below the surface. Okay, so you know that plastic mantle layer. All right, that's where a lot of the flowing happens. I like to think of it like a lava lamp. I actually have one here in the classroom. But a lava lamp definitely models and shows you how that mantle will move. And then obviously in that circular pattern, and wherever you have rising, you're going to have magma kind of seeping out of volcanoes, and then wherever it's sinking, you might actually have something else happening, which we'll discuss in a moment. Okay, so plate tectonics took all the ideas of continental drift and added more. So temperature of the oceanic crust decreases as you move away from mid-ocean ridges. So we discovered mid-ocean ridges by going down in these two-man submarines. One called Alvin, that's the main one that we use. Okay, obviously some other countries have some too, like China, I know. They just got down to the bottom of the Marianas Trench recently. But either way, so ridges basically are underwater mountains. Okay, and in the middle, that's where magma's rising. So the temperature by the ridge is hottest. As you move away from the ridge, it will get cooler. Okay, and that's convection basically below the ridge. You can see it, and there's two convection cells. One moves in one direction, one moves in the other direction. So the plate gets moved apart by that movement. Okay, also the age of the oceanic crust increases as you move away from the mid-ocean ridge. I usually tell my students, or any class, by the ridge, the crust is young and hot, and as you move away from the ridge, it's cold and old. All right, and that's a good way to remember it. It rhymes well, it goes together well, so kind of sticks in the mind. All right, so young and hot, cold and old. All right, also there's a pattern of corresponding stripes on either side of the mid-ocean ridge. All right, we discovered what those were. They were basically a way that the rocks are measuring basically the magnetic polarity of the Earth, right? So where the North Pole is of the magnet or magnetic field created by the Earth. And right now we're in normal polarity, so obviously the rocks, the one side of the rock will be facing north, and in the past it's reversed, so sometimes we see it facing the other direction, and as a result we end up with a pattern of dark and light striping that we can use as a kind of recorder of magnetic polarity changes. Okay, and that happens over time. So how often? Well, again, this is the recorder of the whole thing. All right, we'll discuss this further in class. Okay, so magnetic polarity changes. So here's what I'm talking about, the magnetic striping pattern. So these are facing north, our current North Pole. And then next to it, you see rocks facing the opposite direction with the opposite polarity. Okay, and then again, normal polarity on both sides. This is going to mirror on the ridge, so it's kind of like a mirror image, all right, as you go outward. All right, so just so you're aware of that. Okay, so volcanoes, earthquakes, mountain ranges also occur in specific bands or belts on the Earth's surface. These are along plate boundaries. Okay, most are going to be on the Pacific Ring of Fire. All right, that's where you have most of the volcanic activity. That's why they call it the Ring of Fire. But also earthquakes, volcanoes also happen in those same areas. All right, they're all closely associated with each other. Okay, this is what we call a hotspot. Hawaiian Islands were actually formed this way, right? And that's just one of many island chains throughout the world that were formed this way. Okay, so basically a hotspot is a weak point in the crust where the magma pushes through, and what it can do is it keeps erupting over time, and it can grow into a mountain range that can come out of the ocean. So Hawaii is actually one of the largest mountains in the world technically, because if you go from the bottom of the ocean all the way to the top of the highest peak of the volcanic mountain there, it's one of the biggest mountains in the world. I think it's like third or fourth biggest in the world. All right, now how does this work? How do you make a whole chain of islands? Okay, well, magma's coming up, making the island. So the current one that's has volcanic activity is the Big Island of Hawaii. The other islands that are northwest of it, because that's the direction the plate is moving, they are older, right? So we'll take a look at that. Okay, so here it is. This is the way it works. So obviously magma is going to come up through that weak point. It's going to be an active volcano. It's going to make your mountain in that area, and then which becomes an island. Okay, and then it's going to move out of the way after it stops erupting, and then another one will pop up in its place. All right, so think of it like a conveyor belt of making volcanic mountains which turn into islands. Right, and you can see here, okay, this is an example of that. Okay, so obviously, and this is the result. So currently, this is the active volcano in Hawaii, this island here, the Big Island. Okay, and then if you go this way, these are getting slightly older, these islands, and the oldest islands are over here in this corner. So the plate is moving this direction, upward northwest. If Hawaii stops erupting, all right, millions of years from now, this will move out of the hotspot area, and then a new island will form southeast of Hawaii, in the chain, expanding the island chain more. But this has been the most active volcano. You can see, or volcanoes, I should say. That's why it's the biggest island out of the chain. All right, so same thing. This is just showing you direction of plate movement, northwest. And this Hawaiian chain actually technically goes all the way up this way. Okay, so there's a bunch of other islands, Midway Islands, which may have been connected to that whole plate movement and the hotspot. Okay, now plate boundary types. Okay, so divergent are when plates diverge or move apart. All right, what happens at the divergent plate boundaries? Those are the mid-ocean ridges. Crust is going to be created there. All right, so it's like a conveyor belt of making crust. All right, crust comes up, moves out. Crust comes up, moves out. All right, it keeps creating the crust. So you remember I said cold and old, young and hot. Okay, so young and hot at the ridge. As you move away, cold and old. Okay, there is one instance of divergence on land. This is in Africa. They call this the East African Rift Valley. So there's a bunch of volcanoes in this area, you can see. But also, there's a lot of movement. And so what is the plates doing there? They're moving apart. So part of Africa is splitting apart here, and the result is all these volcanoes. All right, eventually, this will split off and become part of something else eventually. It will be an island first, and then it might collide with something else later on in Earth's history. Okay. Convergence are when two plates collide. The result definitely will create mountains. Okay. What type of mountains? Well, that depends. So what type of crust is doing it? So ocean crust colliding with continental crust. You remember earlier in the chapter we mentioned oceanic crust is more dense than continental crust. So as a result, ocean crust will sink below continental crust. All right, on land you're going to have volcanic mountains. Okay, you'll also have a trench offshore, usually a deeper part of the ocean. So this is the Andes Mountains. I like to use these ones usually in questions. All right, more close to home here. But also they can use other convergent plate boundaries throughout the world, like even the one on the Marianas Trench. Okay, but either way, that's subduction. Okay, the other type, continent to continent convergence, that's continental crust colliding. The result is bigger mountains. Okay, so India, if you remember back to the puzzle piece thing, India was the piece of the continent that moved the most, actually, in the map, if you watched it. All right, and it slammed into Asia. As it did it, the Himalayan mountains grow. Okay, and they're still growing today, actually. They just did measurements recently, and they actually found out that they're actually taller again. So still growing from the crustal collisions. Okay, my third type of plate boundary is a transform plate boundary. Okay, so what's happening here? You have two plates sliding side by side. Okay, it's the North America plate and the Pacific plate here. Pacific plate is moving northwest. North America plate's moving southeast here. As a result, you end up getting a lot of earthquakes in this area. Okay, so that's why California is known for that. Definitely two plates sliding past one another. They'll get stuck sometimes. They get stuck, strain builds up, and then they release that strain, and that's what causes the earthquake. All right. Also, throughout the Pacific Ocean, you see a lot of mid-ocean ridges. Sometimes they'll have a transformed fault between the two ridges. That's why they look like kind of like a ladder in that map on the reference table. Okay, what else can happen at subduction zones? Watch this video. You'll see the slipping of plates. And what does that mean? Well, slipping of plates in a subduction zone is going to cause the movement of the water. As a result, you can get large waves. The waves are as big as from the ocean bottom to the top of the water. Okay, now Out in the middle of the ocean, it might be a little 2-foot bump. When it gets to the shoreline, that bump now will grow because it's just like waves at the ocean. They'll get bigger as they come to the shoreline because basically the water will get bunched up like it basically and grow. Okay, and then it will crash down on the beach. Okay, and it's not just one wave, it's a series of waves. Okay, so it's a series of water waves created by crustal movements, earthquakes under the ocean. Also landslides can trigger them if they're large enough. They move around 300 to 500 miles per hour towards the shoreline, so you must act quickly. They do not become large till they reach the shore. Okay, so in most areas that have tsunamis, you'll see these signs. In case of an earthquake, go to higher ground or inland, and they have actually warning systems in place with buoys out in the water that actually bob up and down when a wave comes after an earthquake, and it can alert people on land at least minutes before one comes, hopefully, if not hours. Okay, because they go out in every direction. Okay, and the Indian Ocean tsunami in 2004 was the largest in recorded history that we know of. Okay, definitely caught everybody by surprise. Okay, and also the Japan one, which wasn't too long ago, 2011. Okay, so 2011 also caused major damage, and so these can be very dangerous, can cause loss of life, definitely will sweep away buildings, you name it. Okay, it's not something you can dive under. It's not like an ocean wave like what we know. It's a surge of water, okay, which moves like a river, and many people drown. Okay, and that's the biggest hazard there. Okay, all right, so that's it for Plate Tectonics Continental Drift. All right, so I'll see you guys next time.